All right, so we're in section 2.1, looking at frequency distributions, histograms, and other related topics. So make sure you check over the section in your textbook. I refer to some page numbers for you to look at. So first, 2.1 concerns what are called histograms, and it's a type of a bar graph in which the height of the bars show the frequency and the width represents some kind of a quantitative value. And so your book takes you through the process step by step, which I've condensed into these notes. But again, check it out in the actual textbook. So how do we make a histogram? This is if you're doing it by hand. It's fairly labor intensive depending on how much data you're looking at. So first, step number one, organize the data into a frequency table. Step number two, decide on the number of classes to divide the data into. Usually this is going to range from 5 to 15. What happens with the number of classes? Those are going to be the bars themselves. And if you make it less than 5 and condense too much information into very few boxes or very few bars, you don't get a lot of information. Whereas if you do too many bars, like again, they say that the range is from 5 to 15, but if you do too many bars, what happens is the data washes out, everything sort of evens out, and you can't really read it, what's going on that very well. Step number 3, calculate the class width. That's the largest value minus the smallest value of your data divided by the number of classes. You're going to run into this again. The largest minus the smallest value is actually referred to as the range, which is a quick measure of the spread of data when we start looking at doing more about investigating the spread of the data. Number 4, calculate the lower and upper limits of each of the classes. Again, they give you a good example in the textbook in this based on, let's see, it's car mileage that people drive in downtown Dallas, going to work type of thing. Step number 5, you tally up the frequency for each class and calculate the midpoint for step 6. That's going to be the lower class limit plus the upper class limit divided by 2. So the midpoint, by the way, is also referred to as a class mark. You might run into that. Number 7, find the upper and lower class boundaries. Step 8, place the class boundaries on the horizontal axis and frequencies on the vertical axis. So you're going to have bars that are going straight up and down. Step 9, for each class, draw a bar with the width equal to the class boundary and the height equal to the class frequency. And then they say this for everything, assuming that you're going to be turning it in or displaying it to somebody. All of the graphs, you'll see more as we go through different types of graphs. They're titled and labeled appropriately. And what I would recommend is read over pages 39 through 42 for the example of making a histogram with that car data. And as always, with the entire course, should you have any questions, you need to email me or something like that, or you want to do questions via Zoom, please feel free to do that. So we have frequency histograms, which you see here on the left, the frequency histogram. And then on the right, we have what's called a relative frequency histogram. Well, relative frequency histograms are constructed the same method as above, except the heights of the bars are relative frequencies, not the actual frequencies. And the relative frequency is going to be the class frequency divided by the total of all of the frequencies. And again, look through your textbook for further information about that. But check this out. So this is something I just got about number of books sold. I just needed some graphs to show you what's going on here. So the frequency histogram we see on the left over here goes from 0 up to 200. Here's your classes 0 to 10, 11 to 20, 21 to 30, and then 31 and up. And those are the prices, okay? So you got the prices going along the bottom, number of books sold. So look at the shape of this particular histogram. The relative frequency histogram, class frequency divided by total, take a look at it. It's the same shape. The only difference is over here on the side, you don't have the number of books sold. You just have 10%, 20%, 30%, and 40%, right? Calculating those relative frequencies. But notice the shape is the same. Relative frequency, by the way, is probability. When we get in the probability chapter, relative frequency is one of the methods you use to calculate probabilities. Well, so for example, the probability that you're in this second class right here where this bar is, where it was from $11 to $20 for the price, 40% were in that category, is how we're reading that. The shapes of the histograms, you're going to need to be familiar with this. But again, remember, you can use your notes and your textbook for all of your tests and for your final exam, okay? So these are the common ones that you run into. The first one is symmetrical. You can fold it in half about this middle bar right here, and it would match up perfectly if it's perfectly symmetrical. In reality, the data you get usually isn't perfectly symmetrical, but it's close enough to where you would refer to it as symmetrical. These next two people get mixed up, so watch out for that. Notice when you're on the far left, you're in the higher bars, and as you go to the right, the number of or the frequencies of those bars get less and less. That's referred to as skewed right. And often people mix up skewed right and skewed left, right? But it's skewed to the tail end of the data. So in this case, it's right. In this case, it starts out with small frequencies and gets bigger as you go to the right. That's referred to as skewed left. The data trails down to the left. So you could see, for example, a question on your test about, describe this shape of distribution, multiple choice, pick out which one is correct. Uniform distributions. Now, this one is not perfectly uniform, but roughly the heights of the bars are the same. So this is referred to as a uniform distribution. And it could be that the heights of all of the bars are exactly the same, okay? But this is approximately uniform. If you have data lumped in two parts, like this next distribution, it's referred to as bimodal. So you see this high point here is on the left and this other one is on the right. And then a random distribution has no real shape. It just goes up and down and up and down, referred to as a random distribution. Other related graphs that you're looking at. Notice the histogram underneath here. And I pulled this off the internet, and I don't know what disease this is referring to, but it's in 2012, and they're looking at cases of disease X by month. You can see that they've labeled the number of cases on the left side of the graph. And on top of that histogram, in red, they have what's called a frequency polygon. And sometimes looking at frequency polygons have an advantage over looking at the actual histogram itself. So what they've done is gone to the middle of each of these bars, found the midpoint, and then connected them with a line segment. So you have a frequency polygon. An advantage of a frequency polygon, by the way, is you can take multiple pieces of data or like multiple histograms, but instead of lying one histogram on top of another one or trying to put three of them on the same graph, you could use different colors of line segments is usually what's done. You'll see another example of that later. You also have something called an ogive, is how that's pronounced. And you're looking at cumulative frequencies. So like you have a frequency for the first dot here at 0 and then at 4, you have that frequency and then you add those together with the other data and you get to the next frequency and so on, and then you connect the dots. This is something about a computer science aptitude test. And so the cumulative relative frequencies are going up. And by the time that you're finished making this ogive, you should be at the 100% mark or 1.0. So that's something that's going to keep raising as you go from left to right. Oh, and I should have had that down more. You're looking at test scores here, is what you're looking at. And that's pretty much it for that section. As far as the homework goes, I would recommend looking at problems 7, 11, 13B, and 13D, as well as examples that they show you throughout the section. In fact, do that for all of your sections. Look over the examples good, and again, if you have questions, please feel free to contact me. Section 2.2, now we're getting in other types of graphical displays of data. Bar graphs, circle graphs, and time series graphs. And so what I have here is something I downloaded from a shark research organization at the University of Florida. And so this is since 1990 all the way up to 2006. So what they've done, if you look at the top, while the graph on the left is for the United States total number of shark attacks during those time periods, and then on the right is Florida. Notice, by the way, from what was that again? 1990 to 2006, they recorded a total of 570 attacks. And then what they've done, and they did the same for Florida here, right? Notice Florida, by the way, out of those 570, Florida has 365 of those attacks. It's one of the highest shark attack places in the United States. So, for example, you're reading this in the year 1990 in the first row here, the total attacks were 18. None of them were fatal. 18 were non-fatal. For the U.S. in 1991, 24 attacks. One of them was fatal. 23 were not fatal. And so, they do the same with the Florida when you can look at this on your own because you have the access to the notes. But the idea is they've looked at this all the way to 2006. Now, looking at a bunch of numbers on tables, depending on how many numbers there are, can get really tedious. So the idea is, rather than have tables like this, to make it a more visual display using some kind of graph to give you information about the data, all right? Oh yeah, International Shark Attack File. If you're into that, they're still in business in Florida, so you look up International Shark Attack File and keep up to date if you wish. Data can be displayed graphically to aid in analysis. So what are some advantages of a graphical display as opposed to a tabular one like what we just looked at? Well, first, graphical displays should do the following. They should show the data. B is important. They should induce the viewer to think about the substance of the graph, what you're going over, rather than the methodology, design, technology, or other production devices that went into making the graph. There's a lot of people out there that try to make a really fancy graph using their computer, typing in data, and they make it so that it's distracting. It distracts people sometimes from actually trying to get information from the data itself. And C, it should avoid distortion of data. It should be accurate. Bar graphs. Bar graphs can be either vertical or horizontal. This is important. You want to make sure the bars are of uniform width and uniformly spaced. The width of the bar should not, like different widths of bars, it shouldn't be doing that. It should be the height of the bar that gives you the information. If it's going straight up and down, if it's vertical, if it's horizontal, it would be the width. Bar length represents the values of the variable frequency or percentage of occurrence. Percentage of occurrence. And the same scale is used for each bar. That's important. Otherwise, it's referred to as misleading data. And then if you're turning this in for something, you'll see that title, labels, and scales are provided to let people know how to read these graphs. So here's a graph of the shark attacks versus population growth over the past decade. The total size, the total number of attacks was 392. This is in Florida. I'm going to reduce the size of this a little bit here so that we can see more information. So this started in 1910 or 1900 to 1910. That's when they first started collecting data about the shark attacks. And so then you can see 1910 to 1920, all the way up to 1990 to 1999 was as far as this went. All of the attacks are in blue and the fatalities are in yellow. All right. And then what they've done is they've put in this population graph to show you how the population was rising in relationship to the heights of the blue bars, the number of shark attacks. And then an interesting thing here also, if you take a look at the yellow bars, that's the number of fatalities. All right. So there was a total of 18. So interestingly enough, the blue bars are raising over time, probably because, there's more people swimming in the water and there's more people in there for the sharks to attack. The yellow bars, though, stay relatively the same. They stay relatively small. So having more people in the water, but not so many fatalities, right? That's evened out with those yellow bars, could be indicative of something like, for example, better emergency services, better transportations for ambulances or EMT or helicopters, some kind of rescue, you know, vehicles or vessels to get to the people in time and get them to the hospital, and could also be better treatment in the hospitals. And by the way, the understanding of graphs to some extent is based on your background information that you might have about the particular topic that you're looking at that graph about, right? So this is important. Now we're getting to misleading graphs. So watch out for this. Watch out for changing scales. They can be misleading to some people looking at the graphs. Misleading graphs. So here's some misleading graphs. The one on the left here. Can you see what's wrong with this particular graph? I'm going to zoom in on here into this. What's wrong with this first graph right here about money raised? Well, and it's fourth, fifth, and sixth graders at some school that were raising money and they kept track of it in dollars. Look at the starting point dollars wise. It's at 530. When you zoom in like that, the difference between these three categories, fourth, fifth, and sixth graders, become greatly separated than what they are in actuality. In other words, looking at this graph, it looks like the fifth graders did more than twice as much sales as the sixth graders, but that's just based on the scale. What you want to do is you want to start it at 0. If you did, you'd see that these bars were much more level if you're going from 0 up to 600 instead of 530 up to 600. So that's a way to mislead people just visually, right? Here's another one. Here's a picture graph where they use like some kind of an object, in this case, Halloween candy collected. But if you look at this, it looks like Michael, because you need to concentrate on the vertical, not on the entire size of the candy corn. In other words, whatever you're using in a pictograph, it should be exactly the same size. And it should be just like if this candy corn, uh, if this was higher that Shayna sold, you know, you would sort of stack pieces of candy corn up to the correct height, but all of the candy corn would be the right or be the same size. But this makes it look like Michael just did an intensely better job collecting candy than Shayna did. But realistically, she's like 17 or 18 and he's like 36, right? But it exaggerates the difference, which is not something to be done with graphs. Unless you're purposely trying to mislead people, like in a sales, you're trying to sell something or something like that. Here's another example of the difference that the scale can make. So these are interest rates from 2008 to 2012. Look at the difference between the heights of the bars in the left graph. If you start at your lowest is 3.140%, and then compare that, what happens if you start at 0 and go up? Well, here, it greatly exaggerates the difference between interest rates. Whereas if you're starting at a scale of 0, you can't even detect a difference with this graph. the graph on the right. So watch out for stuff like that. Here's another type of graph right here that you can run into. It's called a Pareto chart. It's a type of bar graph essentially used to uh, concentrate on things that are important that need to be addressed as related to things that might not be so important. In this case, this is actually from a group of hospitals that got together and were concerned about patient falls. This was back in 2001, so this is from an actual study of a group of hospitals. And so number of respondents are going up here, 0, 2, 4, 6, 8, 10. And what you do is you arrange the bars in decreasing order from left to right. So you see these first three things that were brought up as one of the biggest things to address: fall precautions, keeping the floor dry, housekeeping dry floor, and monitor medications. So patients get on medications, they get a little bit fuzzy, try to walk, end up falling. And then it decreases as far as the respondents that thought these should be addressed, all the way down to night lights, which one person said out of this study. So you want to concentrate, if you have limited resources, on what are the largest or what are the tallest bars representing that you should address. That's where you should be spending more of the time and money, is the idea. And everyone's seen something like this, a pie chart or circle graph. The wedges of the circle display proportional parts of the total population that share some common characteristic. This one I just pulled off the internet looking for a pie chart that I could actually make big enough to read. This is the Milton's family budget. I have no idea who the Milton family is. Anyway, these are easy to read. So their budget, 33% of their money is budgeted to food, 25% to rent, and so on. Down here, 6% to savings, right? But it has to add up to 100%. Then there's a time series graph. The data are plotted in order of occurrence at regular intervals over a period of time. Let's see how far down I can get over this. And honestly, I have no idea, other than number of people. I have no idea what people they were talking about. But it's from 1996 up to 2002. Well, see, here's the advantage of these time series graphs where you're using line segments, is you can put multiple ones of these on the same graph and use it to compare information. And of course, there's a key here. The men have the diamond shapes there. The women have the square shapes here. So you see the men and women overlaid here. And then with the triangle, this is when you add both sexes together. So how do you know which type of a graph to use? What you need to do, I was going to type this out, but I want you to take a look at page 60, because they go through the different types of graphs that we've looked at, and they give you guidelines on, if this is the kind of information you're dealing with, this is the type of graph that you should use. And sometimes there's more than one graph that you could use for the same type of situation. You'll see that when you look at that table on page 60. Here's the recommended homework. I threw in a couple of even problems here. Problem 3, problem 6, part A, 15, part B, and 16. Take a look at those, and as usual with every section for this entire course, go back and look through examples that they work out for you step by step. Lastly, once more, if you need to get in touch with me, please feel free to do so. Thank you. Oops. Stop share. Stop recording.